there were just a handful of kind of things in topic 4 that we need to wrap up before we go on to the next one. And so I'm gonna just start with that. But to recap, since it feels like it's been a minute since we saw each other last. And since in my opinion, this is kind of the toughest section of the class, this topic here. I just want to kind of recap the sorts of things that were new and kind of notable for when you're doing these types of problems. So in this unit, we're doing differential governing equations. So we have partial differential equations that show up here. And they look like this. So we have conservation of mass, also called continuity, and then we have conservation momentum, which is the Navier-Stokes equations. So we get those 3 equations right there, one for each direction. And when you approach a problem, the first thing that you should do is probably draw a picture and give it a coordinate system. I find that that helps organize kind of what the language in the problem actually is, at least for me. The second thing you're going to do is you're going to write down your assumptions. For this unit, some of the assumptions are the same as when we did the integral analysis section, but a couple are new. So steady and incompressible, those hang around just like last time. Steady just means time derivatives are 0, or density doesn't change. Incompressible means, I'm sorry, steady means time derivatives are 0. Incompressible means density doesn't change. The 2 kind of new ones that we saw in this unit are fully developed. So if a flow is fully developed, that means that in the direction that the fluid is moving, there's no change in velocity with respect to that direction. Okay, so if we look at this example that we did, this fluid is flowing down this hill, and we've said down the hill is the x direction. So this means that any x derivatives on velocity are going to be 0. Keep in mind that doesn't mean you can say the partial p partial x derivative is 0. That's not the same. And then typically the other assumption that we're going to make is that the flow is going to be at most 2-dimensional. So since we've given ourselves y and x coordinate system that are kind of in this plane that we're looking at, we're going to say nothing's happening fore aft. So everything in the z direction is going to be boring to us. That means the w component of velocity is 0, and then all of our z derivatives with respect to velocity are 0 as well. Okay, so once we have all of our assumptions listed, you're going to go through all these equations and simplify, and a lot of the terms are going to go away. And the pattern that you will start to see emerge, and this will happen every time, is you are going to get a very much more simplified version of conservation of mass and momentum. Conservation of momentum you'll be able to solve, and then you can use a boundary condition to figure out what one of the components of the velocity is. And then you can use that result to simplify your momentum equations even more. So this will be the pattern that happens over and over and over again. And this part is the hardest part of solving these problems, in my opinion, provided that, you know, kind of separating variables and integrating is okay for you. I would suggest, you know, sometimes students will ask, like, how can I prepare for these types of questions better? If you're comfortable with this math, then I would suggest, you know, pick up a fluids textbook, either the one I recommend for this class or one in the library, it doesn't really matter. Read a bunch of problems and go through simplifying equations over and over and over again. And it'll start to become kind of old hat, and you'll see the patterns emerge once you do it a bunch of times. When I was an undergrad, I would typically, for things like this, I would practice doing this until it was boring to me. And then I felt ready. Okay. Are there any questions kind of just on the overall approach with these problems before I go on? Okay, cool. So the couple things that I wanted to tack on to the end of this example that will be useful. This is not, what I'm going to write next is not just for this problem. These are kind of general definitions. So you will probably find it useful to know the volume flow rate. So we used Q for this, and we calculated this in the last unit too. And if you remember, Q is equal to V dot A. This is for the case of uniform flow, right? In this unit, we generally don't have uniform flow. Otherwise, these problems would be very, very straightforward to solve. So we can also write this with our integral where we're integrating over the area of U dA. Sorry, U dot dA or V dot dA, just like before. Okay, so this is kind of a general definition, and I'm going to apply it to this problem that we just did. So for the previous example, if we want to find Q, we are going to care about essentially the Q that goes through this plane. So I'm trying to draw it like the plane sticking into this slope, if that makes sense, okay? All right, so our height of that area, we go from 0 to h in the y direction. X doesn't matter because the flow is going in the x direction. And then we're gonna have kind of a width W, okay? Okay, so our Q is going to be equal to our integral from 0 to h of U, and actually I'm going to call the width B because W is the Z component of velocity, so I don't want to make that confusing. So this is our width in the Z direction, and then dx. So this is our dA, and then this is our V. Okay. Okay, so let's just, all we need to do next is substitute in what U is. So U is in the red box above here. So we have 1 over mu times partial P partial X rho, and then GX is G sine theta times 1/2 y squared minus HY. Oh, there's a minus sign here that I just did not put in. There we go. All right. This is a curly bracket. This is a minus sign. Okay. And then we have our Z direction width and then dx. Okay. So now I'm just going to integrate this. And fix a mistake. So 0 to h is not in the x direction, right? It's in the y direction. I'd like to tell you that was a test, but it wasn't. I just made a mistake. So I'll just draw a little picture here to remind us. This is x, this is y, and we're going from 0 to h. All right. So all of this is constant with respect to y, so I can just pull that out into the front of my integral. So I'm going to bring out the b as well. So I have b over mu partial p partial x minus rho g sine theta. And then I'm going to integrate from 0 to h of y squared over 2 minus hy dy. All right, and so we can do these integrals. They're not too bad. I'm going to keep along my constant of integration. I'm sorry, my constant in front of the integration. And so when I integrate y squared over 2, I get y cubed over 6. And then minus hy squared over 2. And I'm going to evaluate this from 0 to h. Oh, yes.
Is that partial or partial density for the?
Oh, pressure. This is a pressure term up here. Yep. That one, right?
Yeah.
Okay. Yes. Mm-hmm. Okay. Just so I don't have to write things a bunch of times, when I put in the h, I have h cubed over 6 minus h cubed over 2, which is minus h cubed over 3. I think this is 2/3, right? So I'd make the h cubed over 2, 3h cubed over 6, right? Okay, so I'm going to substitute that back in here. So I have b over mu times g sine of theta, rho g sine theta. So I'm going to swap these two terms because I picked up a minus sign. Minus partial p partial x. And then I have 2/3 h cubed. All right. The other thing that is useful to us is the following. So if we want to find average flow velocity, we're going to denote this with just a bar over the V. So average flow velocity is just Q divided by A. So we would just take our Q that we have before divided by the area, which is just B times H in this case. So this is the general definition. So Q is just this, which we already calculated. And then our area is just B times H. Okay. So nothing too complicated here. These are just useful definitions to kind of have in your back pocket. Any questions on that? No? Okay. I have one more example that I'd like to do. before we move to our next topic? No question? Okay. All right. Okay. All right, so we have a fully developed laminar flow of an incompressible fluid between two vertical plates. So I'm going to start drawing this. I know I've got two vertically oriented plates like so. All right, and I'm going to give this a coordinate system as well. So this is going to be y, this will be x, and then into and out of the page will be z. All right, and okay, so we have this flow that's happening due to a negative pressure gradient in the y direction. So we'll say something about that in just a second. We want to show that velocity is a function of y only. So we're saying that u is equal to 0, the u component of velocity is equal to 0, and we will also want to show that the pressure gradient in the y direction is a constant. Okay. Okay. Oh, and this, sorry, this should be x direction. It's a constant. All right. Okay, so let's kind of mark up our problem with the assumptions that we can make. So we've drawn our picture. Step 2 is our assumptions. So we have a few things that are already given to us. We have that it's fully developed. We have that it is incompressible. And it's not written, but we're going to assume this is steady. Anybody think of another one that might be reasonable? Yeah, let's assume that this is at most 2D. This is kind of already suggested to us by this, like, show the velocity as a function of y only. All right. So at most 2D, since we've drawn our coordinate system like I've shown over here on the board, we're going to assume that the z component of velocity w is 0 and that our z derivatives of velocity are also 0. Steady, of course, means that our time derivatives are going to be 0. Incompressible means that density is a constant. And then fully developed. What are we thinking about fully developed for this example? What way do we think that the flow is generally going? Or in what direction? X, Y, or Z? Yeah, Y. Oh, Y? Okay, yes. Yeah, so we've got flow going in the Y direction. And so that means that I'm going to say in the Y direction, there's no changes in velocity, which mathematically speaking means that Y gradients on the velocity are going to be 0. All right. So our next step is going to be, we're going to do our governing equations. And we're going to simplify them. I'm going to copy and paste the equations. I think you all have extras in the backs of your little note packet if you need them. All right. Okay, so this guy is momentum. And then mass is partial rho partial t plus partial x of rho u plus partial y of rho v plus partial z of rho w is equal to 0. So this is mass. Okay. Okay, so I am going to start simplifying these. Beginning with our first assumption, which was fully developed. So our velocity is constant in the y direction, so I'm going to get rid of all derivatives with respect to y of a component of velocity. Okay, so I can get rid of this, and this, and this. This one and this one. Right. Oh, and this one. Yeah. Next one is incompressibility. So I get rid of density in conservation of mass. This form of the momentum equations already assumes it's incompressible. So that's done. Next, we're going to tackle steady. So I get rid of my time derivative. So I can get rid of d rho dt for yet another reason. And then I can also get rid of all of these time derivatives. All right, and then last but not least, we're going to assume that this is at most 2D. So first, I'm going to get rid of all my W components of velocity. So anywhere W appears, we're saying that it's 0. Yeah. Oh, yeah.
Sorry.
No, you're fine. Good. Okay. So we took care of the W component of velocity. So Z component of velocity is 0. Now we're going to get rid of all of the Z derivatives with respect to velocity. So we can get rid of this. This and this. And that might be all of them. Okay. I'm going to make one more simplification. I'm going to say that gravity is equal to 0 minus G 0, right? So this is our gravity. So this means that Gx is 0, and it also means that Gz is 0, right? Because if you remember, these this version of the momentum equations is set up so that you can have your coordinate system rotated in any which way relative to gravity. Okay, so if you remember the inclined plane example, it was useful to us to have gravity kind of split between the x and the y direction. In this case, that's not happening, so that means that I can get rid of this term and this term. Okay. Okie dokie. All right, so let's write down our simplified version of the equations. So our conservation of mass is just partial u partial x is equal to 0. This is mass. And then momentum is in the x direction, we have rho times u partial x is equal to minus partial p partial x plus mu partial squared u partial x squared. I'm going to scooch this up a little bit so I have space. All right, in the y direction, I have rho u partial v partial x is equal to minus rho g. So gy is minus g. So I'm just substituting that in there. Minus partial p partial y plus mu partial squared v partial x squared. All right, and then our z direction equation is very uninteresting. So we have 0 is equal to minus partial p partial z. Oop. Any questions on the simplification procedure? All right. So at this stage, we're kind of at a familiar point, hopefully. So we have a system of equations and momentum that are quite a bit simpler, but still not solvable for us. So you'll see we have some nonlinear terms in here. We have this, like particularly in the x and y direction, the left-hand side term is very problematic for us if we'd want to solve it in this state. However, we have something very friendly for conservation of mass. We can handle this, right? So we have that du dx is equal to 0. This means that u has to be a constant. All right, and so in order to figure out what this constant is, we're going to use boundary conditions. So let's take a look at our picture. So our u velocity is going to be anything moving in this direction. All right. Typically what happens is when we want to solve conservation of mass, we're going to end up using a boundary condition that will leverage the impermeability idea of our wall. So we're going to assume that since our walls are impermeable, we can't have any flow in that lateral direction. So if we had a component to velocity in the x direction, that would imply that fluid is somehow coming out of our walls or in from the walls, and that's not happening. Okay. So we have that u is equal to 0 at the walls. So u is equal to 0 everywhere. I need another color. Let's see. All right, so since I have that u is equal to 0, I can use that to clean up my momentum even more. So this goes to 0 and this goes to 0, as does that one. Okay, so saying that u is equal to 0 was part of this problem, so that's good. We've already addressed that. And then now our equations become something even simpler. So we have in the x direction, we have 0 is equal to minus partial p partial x. Yeah.
Wasn't it asking the y direction as well?
Where? I did. Oh, I think that's viscosity.
Oh.
This one?
Yeah.
So hang on. This one?
Yeah.
Yep, that's viscosity. And actually, I'm glad you asked because that comes up. So be very careful when you're doing this, especially on an exam. like we do a lot of cancellations in here, right? So I feel like a lot of students are like, kill all the terms, you know. Viscosity is not a U. So just, you know, exaggerate the little tail on the front if with your handwriting, if that helps. But yeah, just be cautious of that because I've seen that come up before.
So can you explain why it was canceled for the X direction?
Oh, that's because this is a U.
I see.
Yeah. So let me see if I can just draw this a little bit better here. There. Does that help? I know it's tough when they're right next to each other and, you know, yeah.
So this is just because they asked you to find this so that way you equal 0. But if there were other questions, you would.
So I will always pretty much force you to do this step because I'll ask you, like, find both components for velocity, for example. So you'll be looking for U and V both. That being said, I would say, you know, once you've kind of gone through several of these problems and followed this kind of cadence of steps, I'm hoping, you know, kind of coming to the conclusion that U is equal to 0 or V is equal to 0, depending on, you know, the geometry, should kind of turn into like a muscle memory sort of a thing, that you'll just do it. Other questions? Okay. Okay, so our x direction equation is very simple, and our y direction equation kind of will become something that looks very familiar to what we've seen before. So we have 0 is equal to minus rho times g minus partial p partial y plus mu partial squared v partial x squared. I want to take a little kind of segue on this partial derivative. So v can be a function of x, y, z, and t. Those are all the variables that it could depend on, just in general. But we have said that this flow is steady, so it's not going to depend on time, right? We said that the flow is 2D, so it doesn't depend on z. And we also said it was fully developed, so it doesn't depend on y. So we know that v is only going to be a function of x, which means that I can turn my partial derivatives into a total derivative. Does that feel okay for everybody? Okay. Okay, so I'm gonna move my minus rho g and minus partial p partial y over to the left-hand side so they can be positive. And I'm also going to divide by my viscosity. And this is equal to total derivative of v with respect to x. And like I did before, I'm going to write this as kind of a two-step derivative to aid in our separation of variables. Okay. Okay, so let's separate our variables. Our left-hand side doesn't depend on x at all, so it's just a constant hanging out there. So I'm going to move my dx, my outside dx, over to the left-hand side. So I have 1 over mu rho g plus partial p partial y dx is equal to d dv dx. So we're just separating variables and integrate. All right, so I'm just going to integrate both sides. I pick up an x on the left-hand side. So I have rho g plus partial p partial y times x, and I'm going to get my constant of integration. And then this is equal to dv dx. This should not be surprising to you. You can put your constant of integration on either side of this equation. It doesn't matter. It'll kind of come out in the wash when you do your boundary conditions, just so you know. I like to keep it on the left-hand side though, personally. All right. So now I'm going to separate variables and integrate again. Okay, so I have 1 over mu times the quantity of rho g plus partial p partial y times x plus c1. This whole thing times dx is equal to dv. And I'm going to integrate both sides of this equation. All right. Okay, so let's do this integral. So I have 1 over mu times the quantity of rho g plus partial p partial y. I'm going to integrate x. So I have x squared over 2 plus c1 times x. And then we're going to pick up another constant of integration c2. And this is equal to v. All right. Okay, we have two constants of integration. So we need boundary conditions to figure this out. Okay. Okay, so remember v is our vertical component of velocity. So I'm going to go back to our picture real quick so we can remind ourselves. We have two walls. Our v component of velocity is going to be in this direction. Any ideas on what we might be able to use? And I should have put this on the picture before, but we're going to assume they're spaced out a distance h. And I'm going to have y start from 0. I'm sorry, x start from 0 at the left wall. Any ideas? What would be happening to v at the wall? We have a no slip condition, which means our velocity has to be 0 at the wall, at both of the walls, okay? So we have a no slip boundary condition at both walls. So we have that v is equal to 0 at x equals 0 and v equals 0 at x equals h. Okay, so let's apply these. So I'm going to call this boundary condition 1, and this one's going to be 2. So boundary condition 1, if I substitute x equals 0 into here and v equals 0, I just get that C2 is equal to 0. For boundary condition number 2, we're going to have to do a little more algebra than that. So we have 1 over mu rho g plus partial p partial y, h squared over 2 plus c1h is equal to 0. So that means that C1 is equal to minus H divided by 1 over, no, sorry. Minus 1 over mu rho G plus partial P partial Y H squared over 2 divided by H. All right, so I'm going to just get rid of the H from the, one H from the numerator and one from the denominator. So this is equal to 1 over 2 mu rho G plus partial P partial Y H. Okay, so this means that I have 1 over 2 mu quantity rho G plus partial P partial Y times X squared minus HX. Okay. All right. So this is the end of topic 4 and the hardest part of this class, in my opinion. All right, so it's all downhill from here. Any questions before we move on to the next one? No? Okay. Oh, I should also mention at this point, the homework for all of this is on Moodle. Has anybody looked at it yet? Yeah? Okay. Has anybody submitted it yet? Oh, good. Okay. Because I forgot to add the little like upload your work question. So I'll do that. And if anybody has submitted it, I'll just make it a separate assignment. So you'll have to, upload it in a different spot. Sorry. Okay. Okay. All right. So this next topic is essentially about the Bernoulli equation. But more formally, it's on incompressible inviscid flow. So incompressible, we've heard about that a whole bunch at this point. Inviscid, you may not have heard of before. Whoops. Inviscid just means not viscid, not viscous. Or we're going to assume the viscosity is 0. All right. So in the last topic that we literally just were talking about, these were our governing equations, right? So for momentum up top, and then conservation of mass or continuity is on the bottom here. So these are our equations that we know and love. If we can say that a flow is not viscous or that the viscosity is 0, that means that we can get rid of these terms, which helps us tremendously. All right, so we get rid of that second derivative altogether, no matter what. All right, and so in this unit, we're using the assumption that our flows are going to be both incompressible and inviscid. Another way or another word for inviscid is frictionless. So if you remember, viscosity is kind of like an internal friction for our fluid, or mu is equal to 0. Those are all kind of the same statement there. And so if we make that assumption, then we end up what is referred to as Euler's equation. So that's a special case of Navier-Stokes equations with these two assumptions. So we have that the divergence of velocity is 0. So this is from conservation of mass. If you remember, this is just how we say incompressible. mathematically. And this translates to partial u partial x plus partial v partial y plus partial w partial z is equal to 0. All right, and then momentum just becomes density times the material derivative of velocity is equal to rho g minus the gradient of pressure. Okay, so when we make these assumptions, especially including the assumption of frictionless flow or viscosity being 0, we can solve an even wider range of flow problems analytically. So with pencil and paper, because we've gotten rid of that pesky second derivative, which opens a lot of doors for us. Okay. Yeah. Yeah.
Is it rho g minus,
This is a gradient of pressure. Yeah, so this is like if you expand this into all three directions, this is partial p, partial x, partial p, partial y, partial p, partial z. That's that term. Yep. Okay, so the cool thing that we get to do now is we can apply that Euler equation along a streamline to end up with the Bernoulli equation. Has anybody heard of the Bernoulli equation before? We all talk about that in 2500? Or no?
I think it's come up, but it's probably been a while. I
Okay,
mean, it sounds.
I'm gonna talk about it a whole bunch, so don't worry if you don't remember. I was just curious if you heard it. And I'm gonna highlight the fact that we are using this application along a streamline. Okay, that's important. But the equation looks like this. So we have, and I'm gonna try and be like obnoxious about how I'm writing pressure and density, so it's very clear because they appear in the same term in this equation. So, so we have pressure divided by density. And when in doubt, just ask me. Plus velocity squared over 2 plus g times z is a constant along a streamline. Or another way to write this is if we have 2 points along a streamline, we can say that the pressure at point 1 divided by the density at point 1 plus the velocity squared at point 1 over 2 plus g times z1 is equal to all of those same terms at some second location 2. So this is pretty simple, right? Compared to what we were doing last time. And so because it's super simple, it's extremely useful, but it's often abused. So one of my main goals when I teach this class is that no one who comes through my class will abuse the Bernoulli equation, okay? And the ways in which it's often abused is using it outside of kind of the context in which it's allowed. So we can only use it if the assumptions that we made to arrive at this equation still hold, okay? So if the assumptions that we use to come up with this are not applicable for the problem you want to use it for, you can't use it. You just can't, okay? Okay, so let's talk about what those assumptions are or the conditions are. So we are assuming a steady flow. We are assuming an incompressible flow. We're also assuming a frictionless flow, as well as flow along a streamline.
So people use the equation, it's wrong.
Oh, yes.
I don't know if it was like, you would like us to use another way, but like it's technically not wrong. I was curious.
No. So this will be, I mean, depending on how close you are to these things holding is kind of a measure of how wrong it will be. The lab that I eliminated from this semester, so in the fall and winter, there's normally 4 labs in this class, is essentially using the Bernoulli equation on a Venturi tube. So have you guys seen those before? It's kind of like a nozzle and then a diverging nozzle, converging, diverging nozzle sort of setup. So you have flow going through a constriction like this, and then it comes back out like so. And so you've got flow coming through here. And then in this experiment, there's a bunch of pressure taps like at those locations, or roughly, okay? The Bernoulli equation works just fine for this whole setup as you're following a streamline through to about here. However, what happens is, and this is the case when you have a diverging nozzle a lot of times, is as soon as this kind of like geometry opens up, you go from a laminar flow to a turbulent one. So then all of a sudden there's like silly business going on in here. And this, if it's turbulent, that is not frictionless.
You could use it up to a certain point.
Yes. So in this lab, you'll find out, like what you do in the lab is you measure the pressure at each of those locations. And you're also measuring the flow rate. So you know the velocity and then you know the pressure. And essentially what you do is you experimentally measure the pressure at all those locations, and then you use Bernoulli equation to calculate or estimate like what you think theoretically the pressure should be. And you'll find out like, oh, my pressure is pretty close here and here and here and here, comparing experiment to Bernoulli. And then over here, absolutely not. For this reason. Okay. So that lab is a kind of a good demonstration of what happens. So as soon as you have turbulent flow, none of this business, okay? Actually, none of the business that's happening in this class, except for a small thing in the next unit. We'll talk about turbulence a little bit, okay? But like generally speaking, except for like flow and pipes that we're going to talk about in the next unit, if something is turbulent, you guys don't have the tools yet to kind of deal with that from this class. And then, so frictionless is kind of a statement of laminar. All right. So if something is turbulent, Bernoulli equation's out. Incompressible flow, we've talked about that a whole bunch. So if you are, this can also kind of arise as like low Mach number statements, especially if you're talking about air. So these are like low speed flows. Incompressible is generally okay to assume, or if you have like water is generally always incompressible just because of the nature of it. Steady, I think we all kind of have an idea of what steady means at this point. And then flow along a streamline. This will be a little more into the kind of semantics of what's going on. So for example, if you have flow in a pipe, we've already in the last unit sorted out that the velocity is generally going to be in a parabola like this, right? And we know from way back at the beginning of the semester that a streamline lies tangent to the velocity, right? So since all of this velocity is headed in the left to right direction at varying speeds, but it's all generally going in that way, our streamlines are just going to be like this, right? Because we're tangent to our velocity vector is only going left to right. So you might be tempted when you're solving, well, I guess I should write this out. So these are the streamlines. So you can use those lines to do a Bernoulli equation analysis. You might be tempted to say, well, but I want to know something about this point, and I'm going to like say this is a streamline. It's not. Okay, so you can't do that. Does that make sense? And I think I've done this every single exam I've ever written for this class. For like the second exam, there will almost certainly be a like problem where you have, I don't know, 4 situations, and it's like, tell me whether or not you can use Bernoulli equation for this. So these are the sorts of things that I like to put in there to kind of assess, you know, like if I'm saying something's turbulent, or if it's something that you know is turbulent, like a waterfall, you cannot use Bernoulli equation for a waterfall, right? Or if it's something that's clearly compressible, like a high-speed jet in the upper atmosphere, can't use Bernoulli for that. You know, things like that. Okay. Does that make sense?
Yeah, that's really helpful.
Sure. Okay, cool. Feel free to ask more questions, because I know some of these things take, you know, some time sitting and thinking about them to really understand the distinction. But there are actually, I don't know, apparently all the social media algorithms just really know me well, but there are lots of memes about like people assuming that they can use Bernoulli and they can't. I should show you some of my favorite ones next time. Anyway, okay, so that being said, pressure comes up in this equation. As you can see, we have pressure over density. So there's a few things that I want to talk about regarding pressure before we kind of dive into using the Bernoulli equation. And the first one is that the pressure that we're using in the Navier-Stokes equations and in the Bernoulli equation is called the static pressure. It's also called the thermodynamic pressure. All right, and this is measured by an observer riding along with the fluid. But there's 2 other types of pressure that are important. The first one is the stagnation pressure, or the total pressure. These are 2 names for the same thing. This is obtained when the fluid is decelerated to 0 by a frictionless process. I'm hoping that you guys have seen such a thing in thermo at some point. So if you have like a TS diagram and you have some process on it, sorry, this should be pressure. So decelerated to 0 by a frictionless process is something like this. So no change in entropy. And this would be your P naught, 1 and 2. I'm not going to ask you to draw these sorts of things. I don't think so, but just for reference to kind of tie the 2 classes together. Okay. All right. So stagnation pressure, this whole like deceleration of the fluid to 0 by a frictionless process is essentially a thought experiment, because how would you really do that, right? So that's what it is. If we neglect changes in elevation, then we get rid of our GZ term that shows up in the Bernoulli equation, and the equation gets simplified to just pressure divided by density plus the velocity squared over 2 is a constant. All right. And so this is Bernoulli with no elevation change. All right, and so we can write this, we can use our Bernoulli equation between some general condition and then down to our stagnation conditions. So we can say that our stagnation pressure divided by density plus stagnation velocity over 2 is equal to P over rho plus V squared over 2. So these are our stagnation conditions. All right, and we know that at stagnation, our fluid's been decelerated to 0, right? So this is 0. Because we have the stagnation means fluid is at rest. Right? Okay, so that means that we can write an expression for our stagnation pressure. That is P0 is equal to our static pressure plus 1/2 rho V squared. So this is our static pressure. And then this term, let's call it orange. This term is referred to as our dynamic pressure. And I'll write it again. Okay, so if we look at that equation, we can see that we have stagnation pressure is equal to our static pressure plus the dynamic pressure. All right, so we have these 3 kind of pressures to keep in mind. And an illustration that I like to use when kind of comparing and contrasting and defining these 3 pressures is when you hold your hand outside of a moving car window. Has everybody done this before? Like you hold your hand outside the car window? Okay, great. So when the car is not moving, the pressure that you feel on your hand is just, atmospheric pressure. That's our static pressure. And then as the car starts moving, you feel that increased pressure on your hand, right? So you've added onto it your dynamic pressure because of the 1/2 rho V squared term that shows up there. And so this pressure that you're feeling on your hand, this greater pressure is the stagnation pressure because you still have that background atmospheric pressure all around your hand, plus you have that added component of the velocity from the car moving. Okay? And if you've not done this, you should do it on the way home.
What was the term? Like, is it now?
Is that good?
Yeah.
Okay. That like little scratch on the monitor is so bothersome. I keep feeling like there's like something on my screen when I look at it. But it's not there. Okay. All right. Okay, so that equation that we had before that relates stagnation, dynamic, and static pressure together, we can solve that equation for velocity as well, obviously. It looks like that. So that means that if we can measure the static and stagnation pressures at a point, then we can also know the flow speed at that point, which might seem just kind of like arbitrary algebra that I'm doing right now, but this is actually the basis for a piece of equipment called a PO static tube that I'm going to talk about in just a second. Okay, so before I get to that one, I have a couple other methods that I want to talk about, but there are a few methods for measuring static pressure. So the first one is, and this is static pressure, remember? So the first one is we put in a pressure tap right here. So this is like we have a tube or a channel where flow is coming through it. And then we have a little pressure tap at the bottom so we can measure our static pressure there. Another method is to have a tube inserted into our flow that has some small holes on the side of the tube. And that tube will lead to either a manometer or a pressure gauge. All right. So this is measuring static pressure. If we want to measure stagnation pressure, what we might do is we again have that small tube, but now we have a very small hole on the nose of it, kind of where the fluid is hitting it. And then that tube will lead to a manometer or a pressure gauge. All right. And so this is going to give us stagnation pressure. If we want to measure both the static and the stagnation pressures, which will give us a measure of velocity of the flow if we have both of those things, what we will do is we can do two different things. We can have kind of this combined situation like I showed before. So this is our this is a plane, and here's our point of interest. So we would put a pressure tap down at the bottom here to measure P. And then we would also include what's called a total head tube. And that will measure our stagnation pressure, P naught. So this is called a total head tube. Or we could get really creative and we could use what's called a PO static tube, which kind of embeds both of these things in one device. So I'm going to try and draw this well, but I've had limited success in the past. Okay, so we essentially have a tube within a tube is what's happening. So we have a tube that measures our static pressure. So this gives us P naught. And then along the outside of this tube, we have another tube that has holes on the sides. That measures our static pressure, P.
Good question. It's pressure tape or pressure tape
Wait, where?
for the dotted line in the middle of the first thing.
Tap, not tape. Thank you. Listen, I want you to know how hard it is to spell and speak at the same time.
Sometimes I can just barely spell without speaking, so I don't understand. It's all right.
Sometimes I'll have like a really successful, like I'll write something complicated and be talking at the same time. And I'm like, oh man, no one appreciates how hard that was. It's like a version of ambidextrous, I feel. Okay. All right, so let's do some examples. Most of the rest of this unit is just examples, all right? Okay, so we are gonna talk about this PO tube to start with. And we're also gonna do some work with barometers, again, just to remind you. All right, so I'm actually gonna draw a picture of this setup before I read through the question. So we have sort of a channel. And we have some tubing. All righty, and there's a fluid in this tube. And the distance between the two levels is 30 millimeters. Okay. And let's see, and then we have our flow is coming in this way. Not gonna lie to you, I'm pretty proud of this drawing. It's better than the previous time I drew it. Okay. Okay, so we have this PO tube inserted into an airflow at standard temperature and pressure with the purpose of measuring the flow speed. The tube is inserted so that it points upstream into the flow and the pressure is sensed by the tube. The pressure sensed by the tube is the stagnation pressure. All right, so this is measuring stagnation pressure. Right? The static pressure is measured at the same location in the flow using a wall pressure tap. So this is our wall pressure tap here. Tap, not tape. All right, if the pressure difference is 30 millimeters of mercury, so this is mercury, determine the flow speed. All righty. So let's talk about some assumptions. Since we're in the Bernoulli unit, we already know what assumptions we're going to need to list in order to allow us to use the Bernoulli equation, right? Okay, so we have that the air is at standard temperature and pressure. We're gonna assume that this flow is steady at the moment that we're measuring it. We're going to assume that it's slow enough flow that it's incompressible. I can't count. 3, 4. Our fourth assumption is going to be that it is inviscid or frictionless or laminar, however you want to say that is fine. And then we're also going to make an assumption that we're going to analyze a streamline. All right. So because we said it's steady, incompressible, inviscid, and along a streamline, that means that Bernoulli is okay. All right. So I'm going to write down the Bernoulli equation. So I have P over rho plus velocity squared over 2 plus GZ is a constant. All right. And we need 2 points and a streamline to use. So I suggest to you, I'm going to use point 1, and then I'm going to call this point down here point 0. Oops, this is point 0. And we know, because we've done it before, when we sort of defined our stagnation pressure, this is a streamline. All right, so we're going to follow our streamline from point 1 to point 0. Okay, so I'm going to rewrite this Bernoulli equation between point 1 and point 0. So I have P1 over rho plus V1 squared over 2 plus GZ1 is equal to P0 over rho plus V0 squared over 2 plus GZ0. Okay. Okay. Since the 0 point is our stagnation point, we know that V0 is 0, right? Because it's the stagnation velocity. That's kind of how we define stagnation, right? We also need to figure out a Z equals 0 location. Any suggestions? Yeah. So like right here?
Yeah.
I like it. So this is our Z, and then this is Z equals 0. Okay, so Z0 is 0. Lovely.
Question, why, most of the reason the zoom's there isn't.
It's actually rather arbitrary. So as long as you're consistent with measuring heights relative to the same Z equals 0, it will all work out in the math. Usually you want to pick it in a place that's convenient. So like a place where you have other measurements from, for example.
In this case, we're all starting at 0. So it's-
Yep, so we're going from 1 to 0 when we do this. And this is kind of a little bit of the trickiness of this problem, because you probably will say to yourself, well, what do I do with like Z1? Because I don't know that distance, right? So what we're going to do is we're going to leverage the idea that our pressure at 1 is the same as the pressure here, if that makes sense.
Yeah.
Okay. Okay, great. Let's see. And actually, for stagnation pressure, these PO tubes, we typically will assume that the difference between Z1 and Z2 in the height of this little tube, we're going to assume that it's negligible compared to the other terms. So let me write a note about this. We're going to assume Z1 minus Z0 is approximately 0. All right. And when we do that, I can solve this equation for V1, which we've already done before, but I'm just going to show it to you again. So we have V1 squared over 2 is equal to P naught minus P1 over rho. I'm gonna multiply by 2 and then take a square root. And then this is density of air. Since we have density of mercury that shows up in here, I'm gonna just make sure it's extra clear that this is air. Okay. So we know that this system is air at standard temperature and pressure, so we know density of air, that's fine. We don't know this yet, right? We need to figure this out. So we're gonna use our manometer to find that. Okay, so we're just gonna use our hydrostatic equation. Right, so I'm gonna use this point, I'm gonna call this point 2. Actually, sorry, no, I'm not. I'm gonna call this point 2. So if we apply our hydrostatic equation between 0 and 2 in our manometer, right? We have that P2 minus P0 actually, hang on. So I'm gonna just write this out. So use our hydrostatic equation at between 0 and 2. Okay? So we know that the pressure at 0 is equal to the pressure at 2, right? Because we're at the same Z location and the same, going through the same fluid. So we know that P0 is equal to P2, right? So we have P0 is equal to, let's actually do P2. So P2 is equal to P0 plus, we have density of mercury times G times H, and our H is this 30 millimeters. Right? Question?
Makes sense.
Okay. Yeah.
So 2 is not actually at the top of the, it's in, it has to be in line with the reserves. Right? That's why they're equal.
Yes. Hang on. Oh, here, this is, I messed something up. Now, did you know? Were you suspicious? So we have our, we have our pressure here. So our pressure at the top is, this is P1, which is applied here, right? So this should be P1, not P naught. Right, so we have our applied pressure at the top plus the weight
Yeah.
of the water. Is that, because you looked like something wasn't correct and you were right. Sorry about that. So does that make sense? So our pressures are equal on both sides. So we know that the right-hand side, where that free surface is, that's our stagnation pressure applied. And that has to be equal at 0.2. At 0.2, we have our static pressure applied at the top plus that column of fluid, the weight of it. Does that make sense? Okay. Okay, so great. So if I put that in here, what we have is that P naught is equal to P1 plus rho density of mercury times G times H. And we're looking for P naught minus P1, right? So this is just the density of mercury times G times H. All right, so that is this. So I'm just going to substitute that into here. And we get that V1 is equal to the square root of 2 density of mercury times G times H divided by the density of air. Sorry for the confusion there. Does that make sense? Okay, when we do problems like this, it's always a good idea to go back and check, now that we have the velocity, what the Mach number is to make sure it wasn't actually compressible. Okay, so when we plug in our values for this problem, we get that the velocity is 80.8 meters per second. So we're gonna check our Mach number. So m is equal to the velocity over the speed of sound. At STP. And this is, so we have 80.8 divided by 343 meters per second. And so our Mach number is 0.236. So since Mach number is less than 0.3, incompressible is okay. That makes sense?
Is it always 0.3?
Yeah, that's the cutoff for if you have a Mach number 0.3 or higher, then you're in compressibility territory.
And this is if you're using hot water.
Oh, right. So well, actually, no, the Mach number, that definition, V over C, always good. What will change, depending on your fluid, is what C is. So you can look up the speed of sound in any fluid at any temperature and pressure. So for water, it'll be a wildly different number because sound propagates more readily through liquids than gases. Okay. Do you guys want a break or do you want to do another example? Do you want more and then a break? Okay, cool. Okay. All right, we have air flowing steadily at low speed through I'm going to highlight some things. So we have steadily and then at low speed through a horizontal nozzle. So So by definition, this is a device that's gonna accelerate our flow, right? That's what nozzles do. And it's discharging to atmosphere. The area at the nozzle inlet is 0.1 meters squared. At the nozzle exit, the area is 0.02 meters squared. We would like to determine the gauge pressure required at the nozzle inlet to produce an outlet speed of 50 meters per second. All right, so I'm gonna draw a picture. So we have a nozzle. All right. We have area 1 over here is known, and then area 2 over here is known, inlet and an outlet. All right. I'm gonna just draw in some streamlines for us. All right, so those are some streamlines. Okay, so let's write down our assumptions. Oh, and we know, let's see, at point 2, we know P2 is atmospheric pressure. And we want to find P1 over here. And we know that the velocity at the outlet is 50 meters per second. Okay, great. All right, so let's write down our assumptions. So we already have steady is given to us in the problem statement. We have low speed. So I'm going to assume this is laminar or frictionless. We're going to also make the assumption that this is incompressible, but we'll have to go back and check. And then we also want to make an assumption that we can use a streamline, right? Okay, so with all of these in place, then that means that we can use Bernoulli. Okay, and our Bernoulli equation looks like P1 over rho 1 plus V1 squared over 2 plus GZ1 is equal to P2 over rho 2 plus V2 squared over 2 plus GZ2.
Question for the assumptions for the STP.
Mhm.
Are we also, we just assume that for pretty much all of them as well?
Standard temperature and pressure.
Yeah. Or is that not needed for?
We can, well, no, that's a fair thing to ask. So especially when we're talking about air, you might say like, well, the density of the air could be changing. Since we're assuming it's incompressible at the moment, we're going to say density is constant. So we'll assume STP unless otherwise told. Okay, but that's a fair question. Okay, so we want to do analysis over a streamline. And then we're also going to need to say something about where our Z coordinate system is because we need to measure Z between points 1 and point 2. Does anybody have a streamline in mind that might be most convenient for us? Yeah, the one in the center. I love it. Good suggestion, Ellen. Thank you. All right, so we're going to pick this streamline. We have point 1 and we have point 2. So since Z1 and Z2 are the same, they just cancel, right? awfully convenient for us. Okay, in the problem, we were also given that P2 is P atmosphere, so I can put this in here. So this is atmospheric pressure. And we were also given that we want to find P1 such that V2 is this. So we know that this V2 is given to us. So we know that, right? We're also going to assume, since incompressible, P1 and P2 are the same. So I'm going to just call this rho. Okay, so I'm going to solve this for P1 minus P atmosphere because we want to find the gauge pressure at P1. That's what this is. All right, so we have V2 squared minus V1 squared divided by 2. And this whole quantity times rho. Yeah,
Isn't the definition of gauge pressure just accepting line? So that's just,
so gauge pressure is, gauge pressure at 1 is P1 minus P atmosphere. So gauge pressure is always you just take the actual pressure and subtract off atmospheric. Yep, so that kind of comes out of this equation because our P2 is P atmosphere already. Does anybody see a problem so far? We know P atmosphere, we know density of air, we can look it up, that's fine. We're given V2. What about V1? We don't have this, right? Any ideas? We were given areas. So we have 2 areas, 1 velocity, and we want to find another velocity. Yeah. So we can use our volume flow rate in has to be the volume flow rate out. That's just another statement of conservation of mass, right? All right, so we have, I'm gonna just write out the full equation. So we have integral over the whole control volume times density plus integral of the control surfaces rho v dot dA is equal to 0. This is steady and incompressible. So this just becomes a sum of v dot A over the control surfaces is equal to 0, right? So we have an inflow at 1, so we have minus V1A1 plus V2A2 is equal to 0, which means that V1 is equal to V2A2 divided by A1. All right, so I can just substitute this in here. I'm going to bring the half outside as well. So we have V2 squared minus V2 A2 over A1 squared, which is just rho over 2 V2 squared, 1 minus A2 over A1 squared. Yeah, sorry.
I think you drew the A1 arrow backwards.
Oh, sorry. Yes, I was drawing just like this is V.
Oh,
Sorry, no, this was misleading. So this is V1, this is V2. Let me do a different color for the areas. This is A2 and this is A1. Is that better? There we go. All right. Okay, so I can plug in everything that I know. I have density of air is 1.23 kilograms per meter cubed divided by 2. Velocity is 50 meters per second squared. So that's our velocity at 0.2. And then we have the quantity of 1 minus, where did I put my areas? Oh, there we go. I have 0.02 meters squared over 0.1 meters squared. And this gives us 1.48 kPa. Okay. We're going to do another example. And this example is about a siphon. So I'm going to draw a picture for this one as well. So we have a tank of water, and then we have a U-shaped tube that's going to act as a siphon. All right. And here's the water level in our tank. Okay, the bend in the tube is 1 meter above the water surface. So we have this is 1 meter. Okay, so the water's coming out the bottom of the siphon as a free jet at atmospheric pressure. So we have P atmosphere down here. We want to determine the speed of the free jet and the minimum absolute pressure of the water in the bend. So we want to find, I'm going to call this point A. We want to find PA. And we also want to find I'm going to call this point 2. So we want to find V2. Okay. Did we understand the assignment? Yeah, okay. All right, so let's write down our assumptions. All right, we're gonna assume that this is gonna be a roughly steady flow. We're gonna assume it's incompressible, it's water, so that's a good assumption. We're going to neglect friction. All right, and then we're also gonna say that we're gonna use streamlines for our analysis. Okay, so because we have made these 4 assumptions, which are all reasonable for this problem, that means that the Bernoulli equation is okay. Okay. And I'm gonna write it down. So we have P1 over rho plus V1 squared over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. Okay? Okay. We want to find the pressure at A, and we also want to find the velocity at 2. Does anybody have any ideas of some streamlines that we should pick out in this example to find those two items? I'd suggest that we find them separately. Which one do we want to find first? Do you want to find PA first, perhaps? Okay. So I would suggest, and this is kind of a little bit of a trick in these types of problems. So I'm going to draw a streamline that starts at the surface of the water and kind of meanders around here and up and through the tube. All right, and I'm going to call this point 1. You can kind of imagine that if this is a laminar flow, that a streamline like that would generally exist. All right. And where should we put our Z coordinate? Does anybody have a vibe on where it should go?
On the surface of the water.
Sure. So this is going to be Z. And so that means Z equals 0 is right here. Okay. Okay, so the other kind of little nuance to this streamline that I've drawn here is we're going to assume that we have a really large tank. And since it's a large tank, it's going to be draining out really, really slowly. And so we can assume that our velocity at 1 at the surface of the water is going to be approximately 0. Okay? Does that make sense? So we're assuming this is a very large, slowly draining tank. Okay? And then because of where it's Dominic, right?
Right.
Okay, because of where Dominic put our Z coordinate system, we also have that Z1 is equal to 0, right? And our surface of our water in our tank is exposed to atmospheric pressure. So we also have that P1 is equal to P atmosphere. Okay? Okay. Okay. On this side of at location 2, which is actually location A, this is going to be PA, which we're looking to find. And then this is VA. VA. And Z2 is 1 meter, right? Yes.
So are you doing this equation twice?
Yeah, we're going to do it twice. Okay, so let's write down what we have so far. So we have that P atmosphere over rho is equal to P at A over rho plus V at A squared over 2 plus GZ2, which we know. We have a slight problem. We want to find this, but we don't know VA. right? So I would suggest, what if we keep our streamline going? So we're gonna keep the streamline going all the way to the bottom. So we're gonna go from 1 to 2 instead, okay? So we still have our left-hand side is the same, so we still have P atmosphere over rho. But now we have P2 over rho plus V2 squared over 2 plus GZ2. All right, let's talk about the right-hand side of this. So P2, it's discharging to atmosphere, so we have P atmosphere, right? We want to find V2. Find this. Okay, what about Z2?
7.
Ah, positive or negative? Yes, so Z2 is negative 7 meters. So always be careful. It doesn't matter where you pick Z equals 0 to be, but you need to be careful with when it's negative and when it's positive. Yes.
I'm confused about everything I'm doing red. Just like how you-
Okay. So here, let me add some more detail. Ah. Okay, so we're starting, I'm going to start with my base Bernoulli equation. All right, so this first time that we did it, we said, let's try going from point 1 to point A. Right, so at the top, the first time we did this, we went from 1 to A, and we found that we have 2 unknowns in that equation, so we can't do that. Or at least it's not super useful to us at the moment. So we said, okay, that's no good. Let's go from point 1 to point 2. So point 1, we still have all the same assumptions. So we have that the velocity at the top of that tank is going to be approximately 0. We're exposed to atmospheric pressure, and then we've set our Z coordinate to be 0 there as well. So we have this is equal to 0. This is equal to 0. And then P1 is P atmosphere, just like before. And then on part 2, we're discharging to the atmosphere. So this is P atmosphere. We want to find V2. And then this is known to us. This is minus 7 meters. Does that help? Okay, fantastic. So I'm going to just rewrite this. So now we have P atmosphere divided by rho plus V2 squared over 2 plus GZ2, which we know. All right, so our atmospheric pressures cancel on both sides. And we end up with V2 is equal to the square root of minus 2 GZ2. And you might be panicking saying, I have the square root of a negative number, but luckily for us, Z is negative, right? So this is square root of 2 times 9.81 meters per second squared times minus or times 7 meters, which is 11.7 meters per second. Okay, so this is part of the problem that we've solved. All right. Oh, yes, sorry.
Why would the Z? Because so like the axis is pointing up and we're kind of traveling downwards for 7 meters.
Yep.
So why does that, when you plug that just in, is it the square and it's no longer negative?
So Z2 is -7.
Yeah.
So I have, here, maybe I skipped a step and it made it confusing.
And I know that gravity would be negative as well, but then you have like a third negative sign.
So this is, I'm glad that you brought this up, Owen. In this equation, G is just the magnitude of gravity.
Okay.
Yes, so G is just like, the magnitude of gravity, no sign. I try to be pretty intentional with this because, this has happened to me as well. In this class, I will leave it as like a vector. But if I'm writing it just like this, I mean magnitude. Okay.
Thank you.
Yes, so in here, just to clear this up, so we still have, from doing the algebra of this equation, we have this minus sign that shows up, right? We have 9.81 is our magnitude of gravity. And then Z2 is -7 meters. Does that clear it up? Okay, perfect. All right, and then we get 11.7 meters per second. Like so. All right, so that's awfully handy. We've figured out one thing. We still want to find PA, and I would suggest that we come back to this equation. So I'm going to call this equation star. I'm going to add a page in here. So now to find pressure at A, we're going to go back to equation star. Okay. So we have that P atmosphere over rho is equal to PA over rho plus VA squared over 2 plus GZ2. All right, I'm going to solve this for PA. So PA is equal to P atmosphere minus rho times V A squared over 2 plus, nope, minus rho GZ2. Right? We know Z2, that's that 1 meter. But we don't know VA still. Does it help us that we know V2? Owen is nodding yes. How?
There shouldn't be velocity change from point A to point B because it's like the same thing.
Yeah, okay, great. So Owen is just basically stating that because of conservation of mass, if the tube is the same size, the velocity at point A and point 2 have to be the same. Does that check out for everybody, or do you want me to write it down, like in terms of the conservation of mass equation? It's good? Okay, so I'm just gonna say because of conservation of mass, VA AA, don't love that, but we're gonna just leave it, is equal to V2 A2. And since the area at A is equal to the area at 2, VA is equal to V2. All right, so now we know everything we need to know. So we have P at A is equal to atmospheric pressure minus rho V2 squared over 2 minus rho G Z2, which we already said is 1 meter. All right, and when we plug in all the values that we have, so we have 101 times 10 to the 3 newtons per meter cubed plus minus 999 kilograms per meter cubed. That's the density of water times 11.7 meters per second squared divided by 2 minus 999 kilograms per meter cubed times 9.81 meters per second squared times 1 meter. This is positive this time. We get 22.8 times 10 to the 3 pascals or 22.8 kPa. What are the feelings on that one? It was okay? Not too bad, right? Okay, fantastic. I have one last example for you. Oh, did I go too fast? Sorry, I can wait a second. Okay, yes.
So. just- Can you go back up?
Yeah.
No, I think it is. It's just, okay, now it makes sense.
It's okay. So this problem, I was just trying to mostly demonstrate that it may be that you need to apply the Bernoulli equation to multiple streamlines to kind of work out the whole thing, and that's okay.
Well, way to make your streamline ones.
Ah.
This one was not too bad.
Yeah. So choosing kind of where the streamlines should go, I would say usually the geometry will help you because you'll know where you're given Z locations with measurements. And then you should also keep an eye out for locations where you know what a pressure or velocities are. So like in this case, at the top of the tank, we could make some assumptions about kind of the velocity and the pressure. And then also at the outlet of the siphon, we were told it discharges to atmosphere, for example, and then we were given a Z location. So that was a good choice too.
Oh, okay.
Does that make sense? So if you think about like the Bernoulli equation, we're looking at pressure, a Z location, and a velocity. So those three things. So sometimes it can be nice to, at each of the points you're considering, like list out what are those three things that you have versus don't. Other questions? No? Okay. All right. This problem has a word that's fun to say. It has a sluice gate. Anyway, I enjoy that word. Okay. A sluice gate. I have to imagine that's like a German word because it feels very German when I say it. I don't know if it is or not, but anyway. Okay, so this is what a sluice gate is. It also sounds a little bit made up. Doesn't it? It sounds like a Dr. Seuss thing to me. Anyway. Okay, so a sluice gate is essentially a gate like this, where we have, when it's down, it's kind of like a dam, and then you can lift it up and water comes out through the crack between the ground and the wall. All right. Da, 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 da. All right, so we have water, and then it's coming out the bottom through this sluice gate, like so. All right. Okay, so we have water flows under a sluice gate on a horizontal bed at the inlet to a flume. So if you don't know, a flume is a really cool experimental kind of apparatus for studying usually like ocean type things, turbulence and things like that. So the flume part of this is essentially like this. So this kind of flow out the bottom is part of another experiment, is the idea. Upstream from the gate, the water depth is 1.5 feet. So this dimension is 1.5 feet. And the speed is negligible. At the vena construct downstream from the gate, the flow streamlines are straight and the depth is 2 inches. So I'm going to call this capital D, and this is going to be lowercase d, and this is 2 inches. All right, we want to determine the flow speed downstream from the gate and the discharge in cubic feet per second per foot of width. All right, so we're also given that the streamlines are straight like this. Okay, so this is going to be V2. I'm going to call this 0.2. All right, we want to find V2, and we also want to find Q2 per, I'm going to call B the depth. Okay. V2 and Q2 are of course related to each other, so we're kind of just looking for V2 essentially. Okay, let's list out our assumptions as we do. So we're going to assume that this is steady. We're going to assume it's incompressible. It's water. That's reasonable. We're going to assume frictionless. Since we're told that the streamlines are in straight lines with each other, that's very suggestive of laminar. So that seems okay. And then we're going to use a streamline. So since we have all of these things present, then that means that Bernoulli is okay. All right. And I've already kind of decided that 0.2 is going to be at our outlet. That's where we want to find the velocity. So as I'm writing the Bernoulli equation for us, maybe give a little bit of thought to what we should use for 0.1. Any vibes? Any opinions on where we should put it?
Top of the water.
You want to put it at the top? Sure. So we could put it, so there's 2 choices that would be reasonable. So we could put it at the top, down to the bottom. Another choice that we could use would be all along the bottom.
Is there like an easier way, or they both about the same?
They are both about the same. Would you like to see them both? Okay. So let's do streamline choice number 1. All right. Okay, so for streamline choice one, we have P1 is gonna be P atmosphere. Right? And we have divided by density. We're gonna assume our velocity at the top is 0 again. And then plus we have G times Z1 and Z1 is D. Yes? Excellent. And then P2, we have, what should we do for P2, actually? We can use hydrostatics to figure this out. What depth are we at?
Oh, 0.5. Negative.
Oh, sorry, at point two. So we want to find the pressure at point two. So we just have that little distance lowercase d
Oh,
of water above us. So I'm going to say P2 is P atmosphere plus rho G lowercase d. Does that make sense? So this is just our pressure at 2. Using the hydrostatic equation. Does that make sense?
yeah, is that not over?
Oh, it still is. Yes, I'm not done.
My
But
bad.
thank you for reminding me. I probably would have forgotten, to be honest with you. All right, we want to find V2. So we're going to leave that as it is. And then GZ2 is just 0 because we called this our Z coordinate and we didn't really talk about it. Right? Okay, so let's solve this. So V2 is equal to I'm going to cancel out, I have a P atmosphere that shows up on both sides of this, right? So I can get rid of that. So I have G rho times G capital D minus rho G lowercase d. That whole quantity times 2. And then I take the square root. Right?
How was it? Rho, times capital?
Oh, I skipped several steps here. So I multiplied through.
The rows cancel, yes.
Oh, I'm sorry. You know what, you're right. I should have no rows on this, actually. This is what I get for canceling or skipping too many steps. There. Does that feel better now? So I canceled out my P atmosphere over rho on both sides. And then the rho G lowercase d divided by rho is just G times D.
So the rho GD, that the rho and that gets canceled.
With the denominator. That makes sense?
Yeah.
Okay, cool. Okay, so this is our answer for streamline number 1. Let's do streamline number 2. Okay. Okay, so we need to do some work for the pressure at point 1, right? So pressure at point 1 is P atmosphere plus rho G capital D. Oops, divided by rho. So this is our P1, right? We're gonna again assume that the velocity is 0 because it said far away from the gate, our velocity is 0. And we also have that Z1 is 0 because we're right at the bottom, right? All right. So that's all we have on the left-hand side. For the right-hand side, we still have our P atmosphere plus rho G lowercase d quantity over rho, just like how we did for before. And then plus V squared over 2. Yes.
Why are you using simplification?
Just to find the pressure. So in order to find the pressure at the bottom of this, we need to know the weight of the whole water on top of it. Does that make sense or no? No? Okay, so we're not told anything about pressure in this problem, except for that we know that it's atmosphere up here at the top, right? And then we know it's atmosphere out here at discharge. All right, so if we want to know pressure down here or pressure down here, we're going to have to use our hydrostatic equation to figure that out. Does that make sense? Okay. Okay, so I'm just going to solve this for V2 again. I'm going to cancel out my P atmospheres because they show up on both sides. All right, and I have rho G capital D over rho is equal to rho G lowercase d over rho plus V2 squared over 2. So these densities cancel. And then I am left with 2 times the quantity of G capital D minus G lowercase d. And then I take the square root of that and get V2. So you'll notice I got the exact same answer. So it doesn't matter. I don't think either one was more difficult than the other. Feel okay to everybody? Okay, cool. Okay. I'm not going to do this. I don't want to do this last example. But I do want to talk about this one last thing, this one last statement about the Bernoulli equation. So we can think of the Bernoulli equation as a mechanical energy balance. And I don't know if it has popped into your mind as we've written it a number of times throughout this class, but we have these terms. These two terms that I have written up here hopefully look a little bit familiar in the sense of mechanical energy. So does V squared over 2 remind you of anything? Perhaps kinetic energy? And then G times Z hopefully is reminiscent of potential energy. And then you can think of P over rho as flow energy. All right, and so by saying that these 3 terms are going to be equal to a constant over a streamline is basically just saying that going from point 1 to point 2, we can kind of redistribute which buckets the energy goes into, but the total amount of energy has to stay the same. Okay. So we assumed to get this equation that we're using an incompressible flow. So we assumed incompressibility and frictionless, right? But those 2 things are actually what link thermodynamic and mechanical energies. So if the conditions are right for using the Bernoulli equation, then we can consider mechanical and internal thermal energies separately from each other. That's kind of cool. All right. And that is the end of this unit. So it's kind of a short one, hopefully a gentler one than the one before it.